Delta, Echo, Foxtrot. How do you remember the NATO phonetic alphabet? This is an alphabet that's used to communicate over radio and just to communicate so the letters aren't confused when you say them, so you're very clearly understood. I was in the military for 8 years. I was in the Navy. And when I looked at this NATO alphabet, I thought, how do I remember that N is November? And then eventually I came to the conclusion, I already know the alphabet, A, B, C, D, E, F, G, H, I. I don't have to memorize the NATO alphabet. Instead, all I have to do is get to the point where I see the letter N, I think of November because I have that in my brain. The N is November. The easiest way that I found to do this is not to memorize the list of the phonetic alphabet, but it's to tell a song, a story. And it's 3 different stories that I memorized that kind of get these words in my brain. Here's the story. Imagine that your name is Alpha, and you say, "Bravo!" to your friend Charlie, who's flying a Delta plane. The plane flies so fast, it echoes. The co-pilot is a fox named Foxtrot. They're flying to play golf, and they stop at a hotel in India and pick up Juliet. Her luggage weighs a kilo. They fly to Lima and pick up Mike in November. And then, with Oscar, their papa, they play in Quebec. That's a story. That's all the way up to Q. Let's say it again. Your name is Alpha. You say bravo to your friend Charlie, who's flying a Delta plane. The plane flies so fast, it echoes. The co-pilot is a fox named Foxtrot. They're flying to play golf and stop at a hotel in India where they pick up Juliet. Her luggage weighs a kilo. They fly to Lima and pick up Mike. They land in November and play with Oscar, their papa, in Quebec. One more time. Your name is Alpha. You say bravo to your friend Charlie, who's flying a Delta plane. The plane flies so fast it echoes. The co-pilot is a fox named Foxtrot. They're flying to play golf and stop at a hotel in India to pick up Juliet. Her luggage weighs a kilo. They fly to Lima to get Mike and land in November. They play with Oscar, their papa, in Quebec. Let's do it again. Your name is Alpha, and you say bravo to your friend Charlie, who's flying a Delta plane. The plane goes so fast, it echoes. His co-pilot is a fox named Foxtrot. They are flying to play golf. They stop at a hotel in India and pick up Juliet. Her luggage weighs a kilo. They fly to Lima and pick up Mike in November. And then with Oscar, their papa, they play in Quebec. That is all the way up to Q there. And if you just say the story in your brain enough times, when you see the letter C, you're going to remember Charlie. When you see the letter F, you're going to remember Foxtrot. When you see the letter M, you're going to remember Mike. When you see the letter O, you're going to remember Oscar. In other words, the letters will be the brain triggers. You don't have to remember O is Oscar. Just remember the story. Now let's remember 2 more short stories. Romeo in the Sierra Mountains is doing the tango in uniform. One more time. Romeo in the Sierra Mountains is doing the tango in uniform. One more time. Romeo in the Sierra Mountains does the tango in uniform. Romeo in the Sierra Mountains does the tango in uniform. Romeo in the Sierra Mountains is doing the tango in uniform. Romeo, Sierra, Tango, uniform. Now let's remember one last story. Victor is drinking whiskey by the X-ray machine in Yankee Stadium with his friend Zulu. Victor is drinking whiskey by the X-ray machine at Yankee Stadium with his friend Zulu. Victor drinks whiskey by the X-ray machine at Yankee Stadium with his friend Zulu. Victor drinks whiskey at the X-ray machine at Yankee Stadium with his friend Zulu. Victor is drinking whiskey by the X-ray machine in Yankee Stadium with his friend Zulu. So, I don't think you need to remember that K is kilo. I think you just need to remember the story and get the words in your head. And then when you see the letter K, you'll think kilo. When you see P, you'll think Papa. When you see M, you'll think Mike. If you remember the stories and get the words in your head. Remember, you are Alpha. You say bravo to your friend Charlie, who's flying a Delta plane. It goes so fast, it echoes. The co-pilot is a fox named Foxtrot. They're flying to play golf, and they stop at a hotel in India and pick up Juliet. Her luggage weighs a kilo. They fly to Lima and pick up Mike, landing in November. And with Oscar, their papa, they play in Quebec. The next story, Romeo in the Sierra Mountains does the tango in a uniform. The last story, Victor drinks whiskey by the X-ray machine at Yankee Stadium with his friend Zulu. I really think if you just say these stories to yourselves a few times, you will get the words in your head. And then when you're seeing a series of letters, you'll remember the words. You don't have to sit down and remember T is tango and S is Sierra. I think that's unnecessary. I will put the NATO alphabet in the description below. So if you want to see all the letters in the NATO alphabet, the radio alphabet, look in the description below. Also in the description, I will put the links to a memory course I have. I have a memory course called Black Belt Memory. I'm a
Ardell 2452, continue Juliet and Mike to Lima Charlie. Monitor the tower 123.85.
400 feet above Atlanta Hartsfield Airport, air traffic controllers oversee the skies of the world's busiest airport. Firing off commands to pilots.
Delta 393 Atlanta ground runway 27 right taxi via Lima, hold short of taxiway Dixie.
They juggle 2,600 landings and departures a day in all kinds of weather.
You can go upstairs and you can look out of that window and you can see nothing at all and still have movement taking place on your airport.
But air traffic controllers can't mess up. Not only are lives on the line, but
this is the ultimate in domino effects. If something's going wrong in Atlanta, or if there are major delays, it disrupts air travel all throughout the country and parts of the world.
Back in February, before COVID was named a pandemic, Raleigh took us up inside the tallest control tower in the country to see what it really takes to be an air traffic controller. This is Atlanta Hartsfield-Jackson International Airport, and these are its 5 runways. And here's the control tower. It takes a rotating staff of 58 traffic controllers to keep the airport running. Pre-pandemic, they directed 190,000 flights through takeoff and landing each year. These controllers are responsible for any planes inside Atlanta Hartsfield airspace, 5 miles out and 4,000 feet above the airport. Once a plane enters Atlanta's territory, air traffic controllers are in charge of communicating with pilots over radio. They direct pilots in the air through safe landings and pilots on the ground through takeoffs. The goal?
Efficiency, efficiency, efficiency. What can you do to help us be more efficient? Well, the one thing that we're not going to do is make sure that you compromise safety in that equation.
But the job isn't easy.
There's a lot of dynamic decisions. If an aircraft is coming into land and they have to go around because of an unstable approach, the weather didn't cooperate, they couldn't get the runway in sight, you have to be ready to make a decision.
To become a fully qualified controller, it can take up to 5 years of classroom, simulator, and on-the-job training. But if they make it, the average controller in Georgia makes $145,000 a year. A job in Atlanta's tower is one of the most coveted ATC positions in the U.S. Candidates go through a rigorous hiring process, which can take
somewhere just under a year. We're getting closer to 6 to 9 months.
Once they've been hired, incoming controllers start on the simulator.
So any new controller that would come here, they would initially come here and do book work, and then follow up with the book work, they would come in the simulator room.
A new controller will do multiple pass-fail scenarios, but on the simulator, they'll have fewer planes to juggle than the real deal in the tower.
Then they'll have an evaluation, and then if they pass that evaluation, they can head up to the towers.
We have 2 controllers working there today. One of them is in training.
There's never really a slow period to speak of.
Though air traffic always picks up in the summer and days before and after holidays. But whether it's Christmas Eve or just another Tuesday, controllers have to stay focused.
I don't know that we want people to be comfortable. We want people to be on edge. We want people to be at the top of their game.
Controllers have to remember and monitor up to 30 planes at once. That's a lot to think about, especially since studies show the human brain can only handle 7 things in short-term memory at a time.
I had about 25 to 30 aircraft all on my frequency. At one time, they're all taxiing out for departure. But once I said, monitor the tower, 123, 185, that's when they got off my frequency. So, at one time, you could have a lot. Then 1 minute later, it could be all gone.
The job's so mentally draining that the Federal Aviation Administration allows controllers to work for only 2 hours before they're required to take a break. To help make their work easier, controllers' jobs in the tower are highly specific. Each runway is assigned either takeoff or landings.
That controller is just focused on that runway, that specific runway and that specific runway only.
The controller who clears planes for takeoff or landing is called the local controller. There are 2 or 3 of them in the tower at once.
This gentleman's working what we call Local 5, and Local 5 is handling, at the moment, all the arrival aircraft coming in from the east.
Then there's the ground controller. This guy focuses on directing traffic on the ground, telling planes which runway to taxi to. So in the case of an approach and landing, it might start with the local control saying this to the pilot.
It'll be Delta 222, runway 8 left, wind calm, clear to land. We'll turn it over to the ground controller as they exit. Delta 222, contact ground 119.2. They'll go over to ground control. Ground control will tell them which direction to taxi to get them over to the ramp.
Controllers have universal rules to follow to make sure everyone is safe. First, there's the lingo.
All right, 1123, taxi ramp, keep moving, traffic behind you, have a good day.
The international language for air traffic control is English.
They also have special terminology, so no 2 words will get confused.
Runway 27 right, follow southwest.
The guys at Chicago O'Hare or PDK or Atlanta Tower say the same things for most of our control instructions. It doesn't deviate, and that consistency is what helps us keep communications down to a minimum.
Minimal talking is important because every plane and every controller
Right, 2452.
share the same radio frequency.
353, follow the 737 ahead.
And they're all in the same telephone call, 15 airplanes here in Atlanta.
Short calls aren't the only way controllers ensure efficiency. These strips help the controllers keep track of all the planes moving through that process. Each one represents a plane. It has the flight number, the airline, the city the plane's going to or coming from, and the departure or arrival time.
Once the flight plan is generated at its proposed time, as you've seen right here, these will print out. This flight Delta 1904 is an international flight. It's going from Atlanta down to Marigot, so Delta 904. And this aircraft here is a Boeing 757-200. This airplane is scheduled to depart at 1542 Zulu. When he departs, he's requesting to go to 37,000 feet. So this strip would then, once it's ready, they place it in one of these strip holders. So you'd find the Delta 904, which is at Echo 9. They place Echo 9 on here and slide it to the appropriate side.
A controller will have 4 or 5 of these strips active at once. This is how they sequence the planes in order of priority.
The passenger doesn't see the bigger picture. The pilot thinks, I'm been sitting here, why? The reason why he's holding is because we're trying to provide that sequence so that we can get maximum capacity out at one time.
Sequencing can help move planes along quicker, but how exactly does it work? Here's an example. If 2 planes are going the same direction, say to San Antonio and Houston, they have to be at least 4 miles apart, so they don't run into each other in the sky, which means time waiting between takeoffs. But if a controller alters the sequence using those strips...
So in this case, this is a west, a north, and a west. This aircraft's going to San Antonio, this aircraft's going to Milwaukee, and this aircraft's going to Houston. So we can depart 6,000 feet down the runway and airborne and roll all these.
That Milwaukee flight can take off right behind the San Antonio flight. And now they've had 3 planes take off in the same amount of time.
It makes a big difference for the ground controller to actually provide a good sequence because it's efficient and the aircraft can keep going at the fastest rate. And that's what we do. And that's our job.
Efficiency means fewer delays.
If there are major delays, it disrupts air travel all throughout the country and parts of the world.
In 2018, Atlanta Hartsfield-Jackson International Airport was ranked the best airport in the U.S. for flight delays, with the highest percentage of on-time departures.
15 airplanes, we're looking at a minute behind one another, so it's not bad, 15 minutes.
Some things are out of their control.
You can go upstairs and you can look out of that window and you can see nothing at all and still have movement taking place on your airport. And then there's days like today, clear in a million, that's what we call it, when it's just a beautiful sunshine day and you can see forever. We can move a whole bunch of airplanes. It's 132 an hour, I believe, is our arrival rate max. On a typical day, we try to stay right around in the 120s.
Controllers also have to contend with inclement weather. Sometimes planes can't land on their first attempt, so they'll have to pull up, circle back, and get in line to land again.
You have to be ready to make a decision. How am I going to get this airplane back up into the air, back over to the next air traffic control facility so that they can resequence them back into our pattern?
Luckily, some technological advancements have made this whole process a lot easier. Remember those strips?
So a lot of this is automated now.
While controllers may still use the physical strips, they also show up on monitors and are automatically sent over to the next controller in the sequence. Also, technology means weather isn't as debilitating as it once was.
There used to be a time when weather would shut your airport down.
But now,
being able to forecast and project when that weather's coming, we're not surprised like we used to be.
We go in the cloud sometimes, and that's when our equipment is all we got.
ASDX, radar, and GPS positioning help controllers track a plane.
We're able to use that technology now to actually separate and identify where those airplanes are legitimately, so we can use the term clear for takeoff even though we can't see the physical runway any longer.
But all that technology doesn't mean these controllers can be any less diligent. They have to be focused and undistracted nonstop. This is the busiest airport in the world.
The number, the volume, I don't think many airports can handle what we do. That's the truth. Ardell 2452, continue Juliet, Mike to Lima, Charlie, monitor to the tower.
Today, we will talk about the Earth and the geographic coordinates system. Now, before looking at more advanced concepts of air navigation, we must first look at the place where we are going to navigate, which is the Earth. The Earth is the third planet from the Sun in the solar system, and its shape is almost spherical, since it has a polar diameter of 12,714 kilometers and an equatorial diameter of 12,756 kilometers. So as we can see, the Earth is slightly flattened at the poles and elongated at the equator, which gives it an oval shape, known as an oblate spheroid. The reason why the Earth has this shape has to do with the centrifugal force it experiences when it rotates on its own axis. This movement is called rotation, and it takes around 24 hours for the Earth to make a complete revolution around its own axis. Now, the points through which this axis of rotation passes are known as the North and South Poles, which are often used as reference in navigation. On the other hand, the side towards which the Earth rotates is known as East, while the opposite side is known as West. Now, apart from this rotational movement, the Earth also moves around the Sun in a movement called translation. It takes around 365 days for the Earth to make a complete elliptical orbit around the Sun, and the orbital plane in which the Earth moves is known as the ecliptic. Now, it is important to mention that the Earth's axis of rotation is inclined in relation to the ecliptic plane. This inclination is around 23.5 degrees, as we can see, and it is responsible for the seasons throughout the year and other phenomena, such as the solstices and equinoxes. These phenomena occur because the solar radiation received by a certain area of the Earth changes throughout the year, which has significant implications for weather conditions. However, we will not go into detail with this. Now that we know some basic facts about the Earth, we can now look at the cardinal points. The main ones are north, south, east, and west. These points are used for orientation and to express directions on the Earth's surface. So let's define them. East represents the direction in which the Earth rotates, and therefore the west represents the opposite direction to the Earth's rotation. The north is the pole on the left when we are facing east, and the south is the pole diametrically opposite to the North Pole. Now, apart from these, there are other points known as quadrantal points, which are the intermediate directions between the four main cardinal points. These quadrantal points are northeast, southeast, southwest, and northwest. And at the same time, these quadrantal directions can be divided even further. For example, between north and northeast we find the north-northeast. Between the northeast and the east we find the east-northeast, and so on. So as previously mentioned, this system can be used to express the direction to a point in relation to another point. Let's look at an example. Here we have 2 points on the Earth's surface. So if we want to express the relative direction from the red point to the green point using the cardinal direction system, then we can say that the green point is to the northeast of the red point. However, if we want to express the relative direction from the green point to the red point, then the direction will be the opposite, since as we can see, the red point is to the southwest of the green point. The same happens with these other 2 points. In this case, for someone located at the orange point, the yellow point is to the north, while for someone at the yellow point, the orange point is to the south. So as we could see, the cardinal point system is used to express relative directions, rather than for expressing exact positions on the Earth. For that, we need a position reference system where each position is precisely and unambiguously defined on the Earth's surface. An example of a position reference system is the Cartesian system. In this case, 2 reference axes are used, with which it is possible to express any position precisely by means of Cartesian coordinates. For example, if we want to express the position of this red point, we can observe that it is located at 4 units on the x-axis and at 3 units on the y-axis, so the Cartesian coordinates for this point would be x4 and y3. So using these axes as reference, we can accurately and unambiguously express the position of any point within the scale, as we can see here. However, something important to keep in mind is that this Cartesian system only works on a 2-dimensional surface, so it could not be correctly applied to the Earth, since it is a 3-dimensional sphere. However, despite this, the system used on Earth is quite similar, since it uses 2 axes as reference and is known as the geographic coordinate system. The geographic coordinates are a position reference system that allows any position on the Earth to be expressed in terms of latitude and longitude, which are equivalent to the units of the x and y-axis in the Cartesian system. However, the difference is that since the Earth is spherical, instead of using linear units as in the Cartesian system, angular units are used. But we will look at this in detail later. Now the important thing is to know that latitude is used to express how far north or south a point is, while longitude is used to express how far east or west a point is. Let's take a closer look at the reference axes used in this system. As in the Cartesian system, 2 reference axes are used from which latitude and longitude are measured. These axes are the equator line and the Greenwich meridian. Now, in order to understand how this reference axes are defined, first we have to look at the definition of great circle and small circle. A great circle is a plane on a sphere which, passing through its center, divides it into 2 equal parts, as we can see in this example. It is important to note that we can divide the Earth in any direction. As long as it is divided into 2 equal parts, we will obtain a great circle. On the other hand, a small circle is a plane on a sphere which do not passes through its center, and therefore divides it into 2 unequal parts. So in other words, any circle on the Earth that is not a great circle will be a small circle. Here we can see some examples of great and small circles. With this in mind, the equator line is defined as a great circle perpendicular to the Earth's axis of rotation, which divides the Earth into 2 equal hemispheres. And if we compare it to the Cartesian system, it would be the equivalent to the x-axis. On the other hand, the Greenwich meridian, also known as the prime meridian, is defined as a semi-great circle that joins the north and south poles and passes through Greenwich in England. This would be the equivalent to the y-axis in a Cartesian system. With this, we have the 2 reference axes that are used in the geographic coordinates system. However, these axes are also used to divide the Earth into 4 hemispheres. This way, the equator line divides the Earth into the northern and southern hemispheres, while the prime meridian divides it into the western and the eastern hemispheres. Now, due to the size of the Earth, it is common to use secondary reference lines known as parallels and meridians. The meridians are semi-great circles that join the north and south poles, and they are measured in degrees in relation to the prime meridian. These lines are used as a reference for the longitude. On the other hand, the parallels are small circles parallel to the equator line, which are measured in degrees in relation to the equator line. These lines are used as a reference for the latitude. The resulting grid defined by the parallels and meridians is known as the geographic graticule or grid, which is often found on maps and charts. Having seen all this, let's now look at the definition of latitude and longitude. The latitude is defined as the angular distance between the equator line and a point on the Earth's surface, measured in degrees, minutes, and seconds of arc. So in simpler words, it measures how far north or how far south a point is. Now, as we can see in the image on the left, the latitude is actually an angle measured from the center of the Earth, where the equator line represents 0 degrees. In this order of ideas, latitude equals 0 degrees at the equator, and it increases gradually until 90 degrees at each of the poles. So then we say that the latitude goes from 0 to 90 degrees north or south. On the other hand, the longitude is defined as the angular distance between the prime meridian and a point on the Earth's surface, measured in degrees, minutes, and seconds of arc. So in simpler words, it measures how far east or how far west a point is. Now, as we can see in the image on the left, longitude is actually an angle measured from the center of the Earth, where the prime meridian represents 0 degrees. In this order of ideas, longitude equals 0 degrees at the prime meridian, and it increases gradually until 180 degrees in the opposite side of the planet. So then we say that longitude goes from 0 to 180 degrees east or west. In these other images, we can more clearly see why it goes from 0 to 180 degrees either side. In summary then, here we can graphically see how latitude and longitude are measured, and why angles are used instead of linear units. With all this information, we should be able to locate any point on a map by means of the geographic coordinate system. Here then we have a world map with its respective reference axes, so to determine the coordinates of a point on this map, we do it in the same way as in a Cartesian plane. For example, let's determine the coordinates for this point. Before proceeding, it is important to mention that the latitude always goes first. So then the latitude for this point would be 40 degrees north, and the longitude would be 100 degrees west. Now that we know how to do it, let's determine the coordinates of these other points. For this other position, the latitude would be 20 degrees north, and the longitude 40 degrees east. For this other one, the coordinates would be 10 degrees south and 120 degrees east. And finally, for this one, the coordinates would be 60 degrees south and 40 degrees west. Now, so far it seems that this system is quite accurate. However, if we zoom in, we can see that between each degree of latitude and longitude there is a considerably long distance. Specifically, at the equator, the distance between each degree of longitude or latitude is 60 nautical miles. This way, we can accurately express the positions where the parallels and meridians intersect. However, if we want to determine the coordinates of an intermediate position, we would not be able to do it precisely. For that reason, in order to increase the accuracy, the sexagesimal system is used. Basically, this refers to the use of degrees, minutes, and seconds of arc in the geographic coordinates. Here, each degree of latitude or longitude can be divided into 60 minutes, which is also an angular measurement unit. So in simpler words, 1 degree equals to 60 minutes. Now, at the same time, a minute of arc can be divided into 60 seconds. With these smaller units, it is now possible to express positions much more accurately. Let's look at an example. As we can see, this scale includes the minutes and seconds of arc between the degrees, so this way if we want to express the position of this red point, we would say that its latitude is 51 degrees, 0 minutes, and 15 seconds north, while the longitude is 11 degrees, 1 minute, and 30 seconds east. In the same way, this other point would be at 51 degrees, 2 minutes, and 0 seconds north, and 11 degrees, 1 minute, and 0 seconds east. With this in mind, let's determine the coordinates for the following points. The point A has a latitude of 1 degree. Now, to know if it is north or south, we have to look at the arrangement of the parallels. If they increase as we move up, that means that the equator line is below us, and therefore we are in the northern hemisphere. Now, in terms of longitude, it is at 74 degrees, and to know if it is west or east, we look at the arrangement of the meridians. If they increase to the left, that means that the prime meridian is to the right of us, which means that we are in the western hemisphere. So in summary, the coordinates of the point A are 1 degree north and 74 degrees west. Now, the latitude of the point B would be 1 degree south, and the longitude is right in the middle between 73 and 74 degrees west. So using the sexagesimal system, we would say that it is 73 degrees and 30 minutes west. Finally, for the point C, the latitude would be 0 degrees and 30 minutes south, and the longitude 72 degrees and 30 minutes west. Let's now look at a more practical example. Here we have a map with the corresponding grid of parallels and meridians, and we must determine the coordinates for the towns of Georgetown, Fairview, and Greenville. So let's start with Georgetown. In this case, we can deduct that we are in the northern hemisphere since the parallels increase as we move up. So the latitude would be 28 degrees and 30 minutes north. Now, we can determine that we are in the western hemisphere since the meridians increase to the left. So the longitude would be 74 degrees and 22 minutes west. Now, for Fairview, the coordinates would be 27 degrees 45 minutes north and 73 degrees 1 minute west. And finally, for Greenville, the coordinates are 29 degrees 21 minutes north and 73 degrees 35 minutes west. Now, the current geographic coordinate system is based on a model called the World Geodetic System of 1984, which was established as the standard by the ICAO for air navigation purposes. Now, it is necessary to develop a geodetic model because the Earth is not a perfect sphere, and therefore the geoid used as a reference in the coordinate system must be adapted as closely as possible to the actual shape of the Earth, as we can see in this example. In the case of the World Geodetic System 84, it has an error of less than 2 centimeters and is used by current GNSS systems such as the GPS. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below.